So, welcome back to my lectures on groups, rings, and fields. Our next topic is on series of groups. We have learned the structure of a finitely generated abelian groups using the fundamental theorem on finitely generated abelian groups. So, we know almost everything about any kind of finitely generated abelian groups. Series of groups is a tool to study the structure of non-abelian groups. So we will start with some definitions, and then we'll come to a result that gives a insight of the structure of non-abelian groups. So the first definition that we are going with is let G be a group, any group. Then a finite sequence of subgroups H0, H1 dash dash Hn of G is called a subnormal or sub-invariant series of groups of G if H0 is the trivial subgroup, and that is equal to H0 equals this, then it's a proper subgroup of H1 and a proper subgroup of H2, etc. Proper N, and this Hn is for G. H0 dash dash Hns are just subgroups of G, and also and Hi is a normal subgroup of Hi plus 1. H1 is any subgroup of G, but Hi is a normal subgroup of J. If this condition is satisfied, then we call this sequence as a subnormal or subinvariant series of subgroups of G, and is denoted by Hi. But if this subgroups are any subgroups, but if these subgroups are normal subgroups of G, so the sequence, the finite sequence I is equal to 0 to n is a normal or invariant series of groups of G if it is a subnormal series and Hi is a normal subgroup of G. Here you don't need that condition. H1, H dash dash dash, Hn, there can be any groups, but the only thing is Hi is normally Hi plus 1. Here each of the Hi also have to be normal subgroup of G. Example. Let us take the first example as just the subnormal series. Of D4, dihedral group of elements 4. See, this has got elements sigma 0, sigma 1, sigma 2, sigma 3, then mu 1, mu 2, delta 1, delta 2. We have already used this example in several places, so I'm not going to explain what these are, the elements are. These are all permutations. Then the series H0 equals sigma 0, this is the identity permutation, and sigma 0 delta 1 and sigma 0 sigma 2 delta 1 delta 2 and the D4 is a subnormal series, but not normal series, because sigma 0 delta 1 is not normal in D4. So here there are this is our H0, this is our H1, H2, and this is H3. There are 4 elements in that sequence. Normal series. So next example, normal series of Z. Several of them, we'll take one of them. 0, then let us take 15Z, then we'll take 3Z, then we'll take Z, is a normal series of Z. Here actually Z is an abelian group, but one thing is for this whole section, though we are developing a tool to study the structure of a non-abelian group, the examples which we are going to consider to explain the concept is abelian groups. Okay, so this is a normal series of Z containing 4 elements. So our next definition is refinement. So definition, let Ki or Kj from from 0 to n, and I from 0 to m be two subnormal or normal series of the group G, the same group G. Then Kj is a refinement of HIs if the collection of all HIs is a subset of the collection of Kj's. For example, in D4, sigma 0 delta 1, then sigma 0 sigma 2 delta 1 delta 2, then D4 is a refinement of sigma 0 comma delta 1, then D4, because this collection is contained in this collection. Another example would be in Z. Another example in Z will be 0. Let's take 60Z, then 15Z, then 3C, then C is a refinement of 0, 15C, 15C, let's see. Okay, so actually this collection, the whole collection is in this collection. That is why we say it's a refinement. This is a non-abelian example and this is an abelian example. Our next definition is the isomorphism between subnormal or normal series of groups. The subnormal or normal series of groups, let's say HI and KJs are isomorphic if there is a one-to-one map between the factor groups hi plus 1 hi of hi's and kj plus 1 kj of kj. Meaning there will be the number of subgroups here and number of subgroups are same, and not only that, the factor groups within this, for every factor group in this subnormal series, there exists another, there exists a factor group here also. One example is this. 0 is a subgroup of Z5, it's a subgroup of Z15. And 0, Z3, C15 are isomorphic. Because first of all, 1, 2, 3, there are 3 elements in this collection and there are 3 elements in this collection, and the factor groups of the first collection, this is our hi and this is our ki, kj. So the factor groups in hi are Z5 over 0 and C15 over C5, and that is C5 and C3. So this is actually isomorphic to Z3. The factor groups in a ki, kj are Z3 over 0 and C15 over Z3, and that is equal to Z3 comma Z5. So both the collection of factor groups have the same number of elements and they are actually same. Z3, there is a Z3 here, Z5, there is a Z5. So the elements need not be same, but still they can be isomorphic. So our main goal of this section is to show that any two subnormal or normal series of a group have isomorphic refinements. Any two subnormal or normal series of a group have isomorphic refinements. Let's do an example here. Let's take hi to be 0, 60z 20C, and Z. These are all normal series of C. Kj is, let us take it as 0, then we'll take it as of 49Z, then C. So these two are definitely not isomorphic normal series. But we can still find the refinements for these two so that they are isomorphic. So the factor groups of Hi are Z, Z3, and Z20. And factor groups of Kj are Z and Z49. So what we are going to do is expand this Hi to include a factor group of Z49 and expand this one to include Z3 and Z20 so that they are isomorphic. So the refinement of this would be, we start with here C, then you have 20C, then you have 60C, then you want to add a 49 to that. So this will become 2940C, then it is this. So this is definitely a refinement of this. And you include Z3 and Z20 here. So that means this will be Z, then you have 49Z, then you have 980Z, then you have 2940C and C. So you have 1, 2, 3, 4, 5. Here are also 5 elements in the series, and the factor group of each of them would be Z, Z3, Z20, and Z49. So they are isomorphic. So that is what we are going to show in this section. So before we come to the main result, we need to establish one lemma, and that is Sasson-Haas lemma, or it's also called butterfly lemma. So the lemma goes like this. Let H and K be subgroups of a group G, and H star and K star be normal subgroup of H and K, then I'm going to write it here, then H star of H intersection K star is a normal subgroup of H star H intersection K, then K star H star intersection K is a normal subgroup of K star H intersection K. Then third one is H star intersection K times H intersection K star is a normal subgroup of H intersection K. The fourth result is this is a normal subgroup, so you can have a factor group. So H star H intersection K over H star H intersection K star is isomorphic to K star H intersection K over K star H star intersection K, and which is isomorphic to this H intersection K over H star intersection K, H intersection K star. The proof is not very complicated, but there are a lot of notations what we want to familiarize with. So let us go one by one the notations what we are using in this and the sub results. So when I say HK, this means that elements of the form HK where H belongs to H and K belongs to K. And we know that even if H and K are subgroups of G, this does not need to be a subgroup. This will become a subgroup when either H or K is normal. And that is what we proved in the last section on isomorphism theorems. So when I say H star times H intersection K star, this means that this is our H and this is our K. So this will be HK such that H belongs to H star and K belongs to H intersection K star. So this is the notation I'm going to use, and we will use one theorem which we established in isomorphism theorem. That means that is HK is a subgroup when either H or K is normal in G. So this result we are going to use extensively here. Okay? So we need to show that each of these are groups. This is actually a product of this subgroup and this subgroup, but always does not need to be a group if you take the product. But here, since H star and H intersection K star are subgroups of H and H star is normal, in H star times H intersection K star is a subgroup. Or you can say it's a group. Similarly, K star times H star times intersection K is a group. Here H star intersection K is a normal subgroup of H intersection K. I'm going to write the reason for this. Here, H star intersection K is a normal subgroup of H intersection K. So what we need to prove is that if X belongs to H star intersection K and Y belongs to H intersection K, we need to show that Y inverse belongs to H star intersection K. Of course, this is a subgroup of this. There is no need for a proof here because H star is subgroup of this, K is itself. So definitely it's a subgroup. We want to show that it's a normal subgroup. See, X belongs to H star intersection K implies X belongs to H star and X belongs to K. Y belongs to H intersection K implies Y belongs to H and Y belongs to K. So then what happens here is XY inverse belongs to H star. Why? Because H star is normal in H, and Y inverse belongs to K because X and Y belongs to K, and that implies Y inverse belongs to H star intersection K, and that implies H star intersection K is normal in H intersection. So that is the proof of this. So H star intersection K is a normal subgroup of H intersection K. For the similar reason, H intersection K star is a normal subgroup of H intersection K. So in here, both of them are normal subgroups. If both of them are normal subgroups, then their product is also a normal subgroup of this. And that implies H star intersection K times H intersection K star is a normal subgroup of H intersection K. So this part is done. This part is done. So the next part is we need to show that H star intersection in H star times H intersection K star is a normal subgroup of H star times H intersection K. The way we are going to show is that we define a map from H star H intersection K to, we know that this is a normal subgroup of H over K, so we can think about a factor group here. So H intersection K over H star intersection K times H intersection K star. We are going to define a map. Actually, we are going to define an onto map. And we are going to show that the kernel of, and this we are going to show that this is a homomorphism, onto homomorphism. Then we are going to show that the kernel of this map is H star times H intersection K star. That means this will become a normal subgroup of this. See, if you have a homomorphism phi from G to G prime, then the kernel of phi is a normal subgroup of G, and that's what we want to show here. Actually, onto is not an important factor here, but it is still an onto function which we are going to define. So the definition of this phi is going to be like this. Phi of an element of this would be hx, okay, equal to x times, that is the coset of this, coset of x on this, of H star intersection K times H intersection K star. This is a coset, left coset of this group. This is a normal subgroup of this, where H belongs to H star and X belongs to H intersection K. And because that is how an element of this group would look like. Now, things to prove here is phi is well defined. Phi is well defined. Okay. So what we do is let h1, h2 belongs to h star, and x1, x2 belongs to h intersection k. We need to show that phi of h1, x1 is equal to phi of h2, x2 if h1, x1 is equal to h2, x2. If we can prove that, then it is well defined. But this implies h2 inverse h1 is equal to x2 times x1 inverse. So this actually belongs to H star, because this is both of them are in H star, so this belongs to H star, and also there belongs to H intersection. So this means that x2 x1 inverse belongs to H star intersection H intersection K. And that implies x2 inverse x1 belongs to H intersection K. H star intersection K. Because H star is a normal subgroup of H. And that implies it belongs to H star K times H K star. And that is this. And that implies x1, the left coset of this x1 on H star intersection K times H intersection K star is equal to x2 left coset of H star intersection K, H intersection K star. So, if you have two elements from here which are equal, like this, h1 x1 equal to h2 x2, then the images are also same, and that implies phi of h1 x1 is equal to phi of h2 x2. So that means it's well defined. Clearly, phi is onto, because for every x we can find an element in H star H intersection K such that it is mapped to that. And the third part we want to prove is phi is a homomorphism. And that is because, let us take two elements, phi of h1 x1 times h2 x2 from here, and that is equal to phi of this h2 and h1 are coming from H star, and it is normal in H. So we can find h1, you can combine these together and make it as h3 x1, h3 x1 x2, and that is equal to, see, this is an element in H star and this is an element in H intersection K. So image of this will be x1 x2, the left coset of H star intersection K, H intersection K star. And definitely that is equal to x1 of H star intersection K, H intersection K star times x2 times H star intersection K times H intersection K star. And that implies phi of x1 x1 times phi of x2 x2. And that implies phi is a homomorphism. Now we need to find out the kernel of this phi. The kernel of phi is equal to the elements from here from H star H intersection K such that phi of Hx is equal to the identity of this, and that is nothing but H star intersection K, H intersection K star. See, this implies Hx belongs to H star H intersection K star. Because H is actually coming from H star, and X has to be from the intersection of K and K star, and which is K star. And that implies H star of H intersection K star is a normal subgroup of H star H intersection. And with that, the same argument, second is also true. Replace H with K and K with H. We'll get this. So what we have shown is that there exists a homomorphism, an onto homomorphism from H star times H intersection K to H intersection K over H star intersection K times H intersection K star, with kernel as H star times H intersection K star. So this map phi is an onto homomorphism with the kernel equal to H star times H intersection K star. Okay, what does that mean? If you have a homomorphism from G to G prime with the kernel K, then K G over K is isomorphic to phi of G, and if phi is onto, this will become G prime. So this implies, what is G here? G is this. Okay, so H star of H intersection K over the kernel is this. H star of H intersection K star is isomorphic to the image of G, or if it is onto, it is the G prime itself, and that is this. H intersection K bar H intersection K H intersection K star. And that is what we want to prove here. And while you can replace K with H and H with K, you'll get this part. What we have proved is this is isomorphic to this. And if you replace H with K and K with H, you'll get this. So the reason why it is also called the butterfly lemma is because if you draw the subgroup diagram, it would look like a butterfly. Let us see how we can draw this. So H and K, probably will write it later. I'm not a good artist, but we'll try. H and K, and you have a H star here, there is an H star here, so K star here. H star is a subgroup of H, and K star is a subgroup of H. And you have a H intersection K, and you have a H intersection H star intersection K times H intersection K star, but we need to do a little up here. H star intersection K, H intersection K star. This is a normal subgroup. Okay, now you have we need to show that this is a normal subgroup. So this is actually here, H star times H intersection K star is a normal subgroup of H star times H intersection K. Similarly, you have a K star intersection H intersection K, and that will be a normal subgroup. This is actually normal subgroup. Normal subgroup of K star times H intersection K. So this has to go a little up. So this will become a butterfly picture here. Okay, so that is why it is called the butterfly lemma.